All right, hi everyone, my name is Ben Calvin. I am a fourth year graduate student working with Mike Fitzgerald at UCLA. I'd like to thank you all for granting me the opportunity to talk about my instrumentation talk in a science meeting. There's not really that much science I'm going to be presenting on. But this is a project that we've been working on for the last couple of years where I am simultaneously operating an adaptive optics system with a controllable segmented primary mirror using a pyramid wavefront sensor. So, as we learned from some talks yesterday, Jerry Nelson sort of pioneered the idea of using a grid of hexagonally segmented primary mirror segments in order to emulate a monolithic primary. But in order to actually do this and get good images, we need to keep all of these segments in line. And the way that we do this at Keck is by using a grid of capacitance-based edge sensors, which are able to electrically detect any physical movement between any two segments that share a common edge. However, recent investigations into how well the system works, led by Sam Ragland starting several years ago, have shown that there are misalignments present on the Keck primaries that are either not sensed or not controlled by these edge sensor systems. And the estimations of the magnitude of these misalignments actually put it at around 90 nanometers RMS semi-statically, which is inducing nearly 200 nanometers of phase aberration into the wavefronts just from the primary mirror alone, which is somewhat of a problem. Additionally, what's worse is that there's reason to believe that these aberrations will actually change with or evolve with the elevation angle of the telescope, meaning that if you are observing over multiple hours, the aberrations present on your PSF will slowly change, which will have trouble for things like astrometry or differential imaging. So we believe there's some reason or sufficient need for us to find some means of monitoring the phase of the primary mirror separate from these edge sensors in order to supplement how they operate. And additionally, when we're looking towards the future, considering ELTs that will have multiple hundreds of segments, we want to find some method that will be scalable for larger telescopes. There are phasing cameras that can be used for the phasing. However, in order to use these, this actually requires you to take time off from your science observations. So we want to find some method that will also be usable in simultaneous operation with science. So what we propose doing is by using the adaptive optics system's wavefront sensor in order to monitor the phase of the primary and eventually effectively incorporate the primary into the adaptive optics system as what we refer to as a controllable segmented primary, or a CSP. And so I've done some simulation work using HCI on modeled after the Keck system and the pyramid wavefront sensor, where I can take the segments. They have the degrees of freedom of piston, tip, and tilt. Each segment can piston, tip, and tilt in relation to the rest of the pupil, and recording the wavefront sensor response. And by stepping through each segment's piston, tip, tilt, we can record each response into a interaction matrix. Inverting this interaction matrix, we get a command matrix that can take any general output from the pyramid wavefront sensor and turn those into commands that will help minimize the signal that's present on the pyramid wavefront sensor. And this would be all well and good, but the first thing that we end up seeing is that there's a lot of overlap between the ways that the CSP can influence the wavefront phase and the way that the deformable mirror influences the wavefront phase. And the pyramid wavefront sensor only generates a single output that has information on all of the phases of the atmosphere, DM, and CSP at once. So we want to find some way for these things to work together so that there's no feedback loop that will cause catastrophic phase problems. And a caveat to them working together is that the CSP does not operate at adaptive optics speeds. We can only change the shape of the primary at maximum of a couple of times a second, whereas the AO system needs to be operating 1,000 times per second. So the way that we get these systems to work together is by just fully disentangling the two. So the way that I do this, as a little visual demonstration, I am projecting out the signals from the CSP that can be corrected by the deformable mirror. So I have the piston measurement from, I think, this segment 7 or something. This segment will generate a pyramid wavefront sensor response that looks like this. A pyramid wavefront sensor that looks like this, or response that looks like this, can also have a similar response from a deformable mirror shape that looks like this when there's no segment induced phase aberration either. So just from the deformable mirror, we can expect the pyramid wavefront sensor to respond as this. And by taking the difference between the two of these, we end up seeing this high spatial frequency signal that's present on the pyramid wavefront sensor that is completely not described by the deformable mirror. So regardless of the shape of the deformable mirror, we will always see this pyramid wavefront sensor response when this CSP piston mode is actuated. And this is described more in detail in a paper that we have that we're writing up by this equation. But for those among you that have noticed, there is a lot of overlap between the signals from this initial CSP mode response and the deformable mirror's approximation of the CSP response. So there's one or two, or before I go into any detail of how well this system operates in closed loop, I want to briefly discuss how much signal strength we actually get. Before I go into that, it's worth noting that when we make the interaction and command matrices based off of these independent modes, we can now fully separate the two systems. So we can have the pyramid wavefront sensor reading out 1,000 times per second, and we can take those wavefront sensor responses and make commands for a deformable mirror just as normal. But then we can also find our commands for the CSP, and we can just hold on to those for effectively significantly longer integration times. And so when we go into testing the sensitivity of the CSP and of the independent CSP modes, which I go into the procedure for how I do this more in detail in my paper, but I compare the signal strength from the independent CSP modes to the anticipated noise sources, which are photon and read noise. And for 30 seconds of integration time on a magnitude 8 star in the H-band, we end up seeing that the vast majority of these independent CSP modes are sensed to below 5 nanometers of uncertainty. I use 5 nanometers as just a benchmark from some of the founding Keck documents for how well the edge sensors perform in general. So this means that we can sense all of our independent CSP, or all of our CSP modes in the independent wavefront sensor space rather accurately. And so now I move into how well I can simulate or how well this behaves in a simultaneous control closed loop setting. So in a different simulation, I put together both the CSP and the AO in closed loop. What I do is I have this, or a general phase aberrated primary to start with. This starts with 90 nanometers RMS phase aberration, which is what we expect to see on the Keck telescope. Then I have a wavefront coming through a somewhat realistic atmosphere being incident on this primary, and then going to the adaptive optics system that is operating at 1,000 times per second to minimize all phase aberrations. And then independently, we have the CSP that's integrating at around 11 seconds. And over 3 simulated minutes, what we end up seeing is that the phase aberrations are almost entirely eliminated, down to below the initial requirements from the edge sensor system to less than 10 nanometers. This simulation is just one of a few that I do in my paper, but I represent through this plot, and I go into more detail on the different takeaways, but the main key takeaway is that as we see a decrease in the misalignments on the primary, we also see a simultaneous large increase in the Strel ratio from the output of the wavefront sensor. We see a nearly 30% increase in the Strel ratio at H-band, which would then correspond to different wavelengths for different Strel ratio increases. This would correspond to about 10% increase in Strel ratio at K-band. And you can actually see this if you're interested in on-sky implementation. Some team led by Maisa Salama and Vincent and Charlotte have used the Zernike wavefront sensor to close the loop on the Keck segments and have shown a consistent increase in the wavefront sensor, or the AO performance. So you should see Maisa's poster if you're interested in that. We also have a bit of on-sky data. So in February of 2022, Sam Ragland took a bit of data from OnSky where he put different amplitudes of what he refers to as L modes. So a few different pistoned segments in an L shape, and we were able to use this data to sense how well this method that I developed operates on Sky. We were able to see that by making an interaction matrix from some of these, we can look at these independent data sources and find a very high accuracy recall using the pyramid wavefront sensor on the other segments, so down to less than 10%. So with that, I'll go to my key takeaways, which is that by actively monitoring the phase of the Keck primary mirror, we are able to increase the performance of our AO system, and this has the potential to improve the PSS stability across observations. Using the independent space of the pyramid wavefront sensor, we are able to sense down to 5 nanometers of accuracy for the majority of pyramid wavefront sensor use cases, and we will be beginning on-sky testing through the Keck Visiting Scholars program this fall. With that, I will take questions.